Yes. So this is my these are my slides. So this is the
Yes, it's visible, sir. Only
good
thing is
morning.
you can make it big.
Yeah. So is it okay? Is it big enough?
Yes, no, sir. Actually, you can bring it in the play mode, sir. Like,
No, play mode, there is a problem because then I cannot introduce some new slides and all that. Okay.
okay, fine, sir. This is enough, sir. This is sufficient, sir.
I think I will rather increase the font size.
Yes. That's fine, sir.
Next.
So people are asking when will we receive the credentials of Qsim?
Credentials that CDAC knows. I don't know. So that is up to CDAC actually.
Yeah, I think like it will be addressed by Vandana Chaturvedi during the sessions.
Yes.
You may
Yes.
kindly wait, sir.
Yes. So I will not be. I will. That's why I am not starting Qsim this week. I will start next week. Today I will do show some backends of the I'm like this Qiskit thing.
Sure,
And
sir.
then
Sure.
we will next week we will be doing more on Qsim and see the errors and all that. By that time, I think everyone will have their credentials.
All right, sir. All right, sir.
Okay. All right. Hello. Almighty, when will we get those lecture notes? So we will post the slides to yesterday's annotated slides and today's things. We will post it immediately after the lecture. And Sudarshni, are you able to hear, sir? Acha, okay. So, all right. I think some people can't hear us, so let's see. Check out your system. So it seems that
Sir, you
Sir,
are
that
sir, you are audible. Probably
okay. Yeah.
need to check their mics or something.
Yes. Many people are saying that they can hear us. Some people cannot hear us. Sriram, good morning. Audible.
Not able to hear, they should just disconnect and connect again. Then they will be able to hear.
Yeah. And now people are able to hear. Yeah. They're just listening to the chat actually.
One small announcement I want to do that if we will upload any study material to the GitHub repository, we will mail the same to everybody for as a notification.
All right, very good morning to everyone and welcome to our second day, Sunday morning. And so the point is that we will get, you will get all the material and please feel free to ask for them or send your comments. We will eventually be listening to them. Now see, this is the second day. This is the second day of the first week. Now the question that many asked last week, yesterday, that which book to study. So there is one book that is very famous, that is by if there is one book that is very famous, that is called that is by Nielsen and Chuang. So I'll write the name over here. I think it's called quantum computing, right? Quantum information and computing. All right, so it is a very famous book, and it's a standard book. There is another book. This book is called Quantum Computing: A Gentle Introduction. Here, this is written by Eleanor Riefel and Wolfgang Polak. And I find this book very informative, and as a first reading, so as the book says, it's a gentle introduction. It's really a gentle introduction, and I have always found this book very good. So both the books are nice, and for first reading, I would prefer this book, and our slides are based upon this book. So now let us move forward. Now let us see what we have done in the yesterday's class, because we have talked a lot about many things, but the question is that what to remember to proceed ahead. First of all, what we said is that you have something called a qubit, so we should not forget that there is something called a qubit, which is called a quantum bit, and state of a qubit. So a state of a qubit is written as a vector ket psi. So it is written ket, K-E-T, not K-T, ket psi. Yes, Vishwadit Barik, that is exactly what I am doing. So ket psi, and ket psi is A ket 0 plus B ket 1. So this is ket 0 and this is ket 1. I know this. And what are A, B's? So A and B both are complex numbers, and they have a relation between them, that is mod A square plus mod B square should give me 1. Oh yeah, so yes, physical interpretation of A and B, we will slowly know these things. I mean, this is what we are doing. So all right, so I know that this is a state of a qubit, and then I also know that ket 0 is a short form of the vector 1 0, and ket 1 is the short form of the vector 0 1. That's also what we know. So we have built up what we have done. This is the qubit state. And then what did we do? We talked about, at length, we talked about inner product. All right. And now, so what is an inner product? So we saw that suppose ket psi is equal to A ket 0 plus B ket 1, comma, ket phi equal to C ket 0 plus D ket 1 are two single qubit states then their inner product bracket phi psi is equal to A conjugate C plus B conjugate D. We also define something called norm of a vector, that whose square is, or let me write this. Don't have to take the square. The norm of a vector, which is square root of the inner product of psi with itself. So bracket psi psi, and that's going to be mod A square plus mod B square. That's also there, and of course this is equal to 1 if it's a quantum state. and that's it. And then we also talked about one thing that is called orthonormal basis. So we talked about basis, dimension, and particularly orthogonality and orthonormality. So this is what we did in the last class, and now we will move forward. So instead of showing the slides, I will write down what I want to say, and then we will go back to the slides and see that those things are written on the slides. So now the point is that suppose you have a qubit state, and then Bishwajit, you wrote something that you said that say last line. So what do you want? Can you type again? What exactly you want to know? All right. Anyway, so let us start here. So what I wanted to, yeah, I will tell that. Right. So the point is that, okay, physical. I will say the physical thing. So basis dimension upward. Oh, so Vishwadis has told this. So basis dimension upward, basis and dimension I have told, right? What is a basis? So roughly speaking, if you have a bunch of vectors, that's smallest number of vectors in a vector space that can generate the whole vector space, that can as linear combinations, is called the basis of that vector space. And number of elements in the vector space, number of elements in a basis is called the dimension of the vector space. And orthogonality and orthonormality, if I say there is an orthonormal basis, that means it is a basis, so it is a bunch of vectors such that all vectors can be written as a linear combination of those vectors. And not only that, if you all the vectors themselves are of length 1, so the inner product, if you take the inner product of each vector by itself, you are going to get 1, and they are mutually orthogonal. So if you take one, okay, so I think I will talk about basis once more. So I will let us talk about a very specific case. I don't know. Let's talk about a vector space first, right? So suppose V is a vector space over complex numbers. All right. So these are vectors. In our case, this V is C cross C. Now, in our case, what I am saying, now let us say what is the basis of this. If we can find two vectors such that, I mean, a set of vectors that can generate all the vectors in C cross C is called a basis of C cross C if that set is the smallest possible set. So you will need, so can you generate C cross C as linear combination by taking one vector? No, you cannot. But if you take two vectors which are not a complex multiple of other, then you will be able to generate all vectors there. So all vectors in C cross C. So for example, if you take K0 and K1, K0 being this vector 1, 0 and K1 being this vector 0, 1, we see that if we have any element AB, I can write it as A 1, 0 plus B 0, 1. All right. So that means that it is a basis. and I cannot do this with one element, okay, one vector. So, and if you now take inner product with 0 0, you will see this is 1 0 and 1 0, so you will get 1. Inner product 1 1, this is 0 1 and 0 1, it is also 1. But if you take inner product 0 1, you will get 1 0 and 1 0 and 0 1, so you will get 0. Inner product 1 0, you will get 0 1 1 0, so this is 0. So that means that this is a ket0 comma ket1 is an orthonormal basis of C cross C. So there are other orthonormal bases of C cross C. For example, I told that ket plus is this and ket minus is this. So if you consider the set ket plus, ket minus, then we will see that I can write any AB as a linear, any vector AB as a linear combination of ket plus, ket minus. We can do this by a kind of simple algebra, and we can also show that it is also orthonormal. So it's also another orthonormal basis. So like that, there can be bases. Now, if someone knows basis and dimensions and all, that's fine. If someone doesn't know, I think for whatever we are going to discuss, it's more or less enough. Yes, it's just like that. If you consider the quantum state space, then it is actually, it is exactly like the usual linear algebra kind of thing. All right, so you will be able to generate. So suppose you have got a basis of the state space, like you have got the single qubit state space. Now, suppose you have a basis for that, then all possible states can be written as linear combination of those states, those basis vectors. So that is exactly where we are starting our discussion. So see, suppose that we are, so the question here that we will ask, so just don't let me talk for 2-3 minutes. After that, please post your questions. So see, I am going to talk about measurements. Now the question is, what is measurements? So essentially, I have a qubit state. So suppose I have constructed a qubit state. How a qubit state can be constructed, we will tell, and we will also construct many particular qubit states using the simulator shortly. So suppose I have a qubit state, and suppose that qubit state, so first one, I have a qubit in the state ket psi equal to ket A 0 plus ket B 1. So this is something that I have. Now I have, how do I, so the question is that how do I know the qubit state if someone doesn't someone hasn't told me that before? Now what the theory says that I can measure the state. The theory states that I can measure the state. So that is called a measurement. So you will have a measurement device. So we need a measurement device to measure. Now you will be surprised that this the connection between mathematics and physics here. So what physicists tell us that a measurement process or a measurement device and whatever we do is intrinsically related to a orthonormal basis. Any measurement process is related to a orthonormal basis of the quantum state space. So I write another thing. Any measurement process is related to an orthonormal basis in the quantum state space. All right. Now the point is that how, let us say, suppose I say, okay, I give you an orthonormal basis. Suppose I give you the orthonormal basis 0, 1. So then what is the measurement process corresponding to that? The point is that if my measurement process is connected to this orthonormal basis, now if I take a qubit and measure the qubit with respect to this basis, then my outcome of the measurement will be either Ket 0 or Ket 1. So let me write this. If we measure the qubit psi with m, that is the measurement process, our outcome or the outcome of the measurement is either Ket 0 or Ket 1. So that means, think about this situation. I have a qubit. I do not know the qubit state. I want to measure it. Whatever I do in the measurement of a single qubit, that measurement process is related to a orthonormal basis. So suppose that orthonormal basis is Ket 0, Ket 1, that particular orthonormal basis, that it is orthonormal, we have studied here. It is in the slide, you can check it after the lecture also. So this is what you know, what is orthonormality, you know what is basis in case of this two-dimensional space over complex number. Let us suppose that is called the basis. Now, so that you will ask me a question that if I take this Ket plus Ket minus, do I get a measurement? I will say yes, you will get a measurement. You will get a measurement corresponding to this basis, you will get a measurement corresponding to this basis. Then you will say, then what is the measurement? The measurement is a measurement. So if you measure, what will you expect? That if I measure something, I expect that I will get a result of the measurement, right? Now, what is the result of the measurement? So what is the result of the measurement? The result of the measurement is one of the basis vectors. I mean, in this case, when you have got two choices, if I measure psi, which is Ket A, if I measure psi, which is Ket A, wait a moment. if I measure psi, which is, let us say, A Ket0, B Ket1, my measurement outcome will be, sometimes it will be Ket0, sometimes it will be Ket1. So my measurement outcome is not deterministic. Now see, gradually we are moving to a very, very strange area where I am saying that my measurement outcome is not deterministic. All right, so here I am. So I am over here now. Let me remove this slide. This slide is better. So see, I have psi, this is A Ket0 plus B Ket1. I have measurement. I am writing the measurement, I am writing by M. This the basis corresponding to the measurement is this. So the outcome of M is either this quantum state or this quantum state. So it kind of, you had infinite number of possible quantum states, but when you measure, you get either Ket0 or Ket1, if the measurement basis is Ket0, Ket1. So you will ask me now, so measurement, outcome of the measurement is not deterministic. Outcome of a measurement is not deterministic. Okay. Now we'll ask that, then okay, fine, then where is the state? Sometimes I will get Ket0, sometimes I will get Ket1. What is the, I mean, what is happening? Now we will say that, look, the point is that if you are measuring Ket psi, what I can say that the probability of that the outcome of the measurement will be Ket0 is obtained by taking inner product 0, Ket0 and Ket psi. So the probability of obtaining, just one moment. Ket0 as the measurement result, measurement M result is inner product 0 psi. What is this? This is C. I am taking this inner product, and this state is Ket0 plus B Ket1, and therefore I can do this. Since it's the inner product, I can write A 0 0 plus B Ket01. Now we have already seen these results. We have calculated these things. If you look at this, 0 0 is 1, 0 1 is 0. So we come back over here. So this is 1. So it becomes, wait a moment. I think I've something. Sorry, probability of obtaining the measurement result is this mod square. So this, take the inner product, take the mod square. So you will get this. So this is mod A into 1 whole square, that is mod A square. Now the probability of obtaining Ket1 as the measurement M result is, now take the inner product with 1 and take the square of the modulus. So it becomes ket1 a ket1 a ket0 plus b ket1. So that gives me square. So it gives me a times 1 0 bracket 1 0 b times bracket 1 1 whole square, and so this gives me a square. And see here, this is what people, I mean, there were some questions. If it is a valid quantum state, then we know that this thing will happen. So that means what we have got is that, so that in a way, this is where theory kind of kind of reconciles with everything. So see, the coefficient mod square, this is will add up to give you 1, and the measure. So, and I was telling that measurements are either you will throw a measurement at ket0 or ket1. What are the probabilities? Take the inner product and take mod square, because inner product in this case is a complex number. Take the modular square of that complex number, you get 1 probability, and the other probability with the other vector, and we are assured, because it's a valid quantum state, that both these probabilities add up to give you 1. Now ask me questions. Nilotpal, Tonoy, what physical quantity we are measuring? We are measuring the quantum state of a qubit. So y square of inner product gives probability. This is how the theory works. I mean, there is no y. So this is how the theory, the quantum mechanics theory was prepared. Y square is taken, sir. Y square is taken, this is mod square. That is how the theory works. When we measure the qubit, do we also get any information about? Yes. Jyoti, can you read the previous? Are you able to see these things? Right? I'm unable to see. Sir, why we need to measure qubit state? Dharmesh, no, it is not a really a dumb question. The question is that we need to measure a qubit state because we need to read a qubit. Because if we are storing some information in a qubit, then we have to learn the information. So here what we see is that it's very difficult to learn I mean, this is the only way we can learn what is in the qubit. So for example, I have got qubit a ket0 plus b ket1. If I measure with respect to ket0 ket1, I know mod a square type, more or less with probability mod a square, I'm going to get ket0, and with probability mod b square, I'm going to get ket1. That's why. Qubit says as in sense of polarization, yes. If a qubit has infinite state, then theoretically it can store infinite amount of information. Yes, of course. But you can't retrieve the information, because if you want to retrieve the information, then you have to measure it. So the whole thing again collapses into 2 possibilities. So that is the point. Usman, for the first case in the slide number 31, isn't b multiplied by 0 as per slide number 31? Isn't b first case? Yeah, it is multiplied by 0, so it doesn't appear here. It's mod a square. Yes, true. This is 0. Another question, Mirza Beg. Actually, I'm sorry, I can't actually able to. Actually, I can't. It is, yes, I am. I don't know how to.
Okay, then.
But you can come here. So these things are coming, but I can't see why we kind of.
Yeah. So what you have to do is
I can take it upstairs. Yeah. So, shall I even? Yeah. Chat. Now I can see the chat. Yeah. Okay. Yeah. I had a trouble with looking at my chats and also now I can see the chat side. Yeah. So I am back again and I can see the chats now. So I think why it's so overlapping window? Okay. Okay, no problem. So let me go back a little bit. I will get used to these things more. Yeah. So let us see the last comments, right? Sir, is there any difference? Yeah, yes, we have proof. Yes, we saw that. I mean, the things are theory is such that any quantum state is a superposition while measuring. Yes, these are all superposition states. Is qubit always superposition state? Superposition depends on the basis with respect to which you are writing the qubit. So after that, let's see. Inner product is a generalization of dot product. Partho, there is a AB represents amplitudes of the states. Yes, of course, these are the probability amplitudes in quantum mechanics. Of course, yes. With measures, are we able to determine what's in the we cannot never completely we cannot always determine exactly what is the quantum state, but we get kind of a sample and with two possibilities. Yeah, so this is about Samarko Banerjee. So Samarko said that if we cannot retrieve more than two states on measurements, how is it better than classical computing? And in my opinion, that is the foundational question, that I have got a very restricted system. I mean, I can write, okay, I can store a lot of information, but I can't retrieve. And still I say that I can do something that no classical machine possibly can do. So that is what we are going to cover in this case course, that what is the benefit, what we can do. And Sudarshini says that, so when we consider more vectors, will the outcome have more probabilistic elements? If yes, it will not lead to a more ambiguous result. Yes, of course. I mean, if you have got a multi-qubit scenario and if we are measuring multiple qubits, then things will be more complicated, definitely. And Ankita says, Ankita Jaiswal says that, sir, why are we using complex numbers for A and B? You know, that theory kind of is like that. I mean, it's without complex number two, the theory doesn't work. And there are some papers that shows that why you can't do it by using only real numbers, but it's for another time. Tonoy De says that, sir, please comment on eigenvalues of qubit states. I will defer doing that for quite a while. After that, I will do. All right. Because eigenvalues did not produce qubit states. Qubit states, to represent them, we use eigenvalues and all that. So that's a different question. All right. I think now we can kind of start doing whatever we are doing. Yeah. Yes. Indrajit, can we generalize it into something? He said something. Let me see this. Indrajit Kundu says, can we generalize it to n-dimensional complex plane? Of course we can do that. If we can do complex space, yes, of course. And that's going to be cool. Usman says that is the orthonormal basis for measurement M is unique? No. You can take any orthonormal basis in principle and construct a measurement in principle. In theory, maybe some restrictions. Tonoy says, I think complex number is a whole set of numbers of real numbers. Okay, anyway. Sir, once we measure it, it will persist. Yeah. Sri Ram. Quantum math there is nothing called quantum math actually. So it's the same math, conventional math. There is something called quantum mechanics, quantum physics. All right. Yeah, in a way, what Joseph says is correct. All right. So let us say one thing that that was rightly pointed out, and I did not point out that thing. So let me remove the chat probably. All right, and let me kind of do this. Yeah. So let me move on a little bit. So see, the point is that what happens that after you measure, so suppose that we have measured the quantum state ket psi is equal to A ket 0 plus B ket 1 using the measurement M having the basis ket 0 ket 1. All right. If the result of the measurement is ket 0, then the quantum state psi has already changed to ket 0. If the result of the measurement is ket 1, then the quantum state psi has already changed to ket 1. So that is the point that was mentioned by some one of you from you. Yeah, what happens to the state? The state is no more. The quantum state psi is no more after you have measured with respect to the particular measurement basis. Whatever is the measurement result, the quantum state changes to that. So that is the reality. That is a theory that to explain the reality. You may say that is what happens. People have seen that. Now see, I have written on my slides in very systematically all the things that I have told just now. So I will move on, and I have given examples here. For example, this is the measurement of psi. And for example, if you want to measure with respect to some other basis, you can do that and you will get things like this. So I have done that. You see that you are getting different measurement results. Okay. And after this, the slides will be, after the end of this lecture, all these slides will be there. I have given the formal mathematical definition of inner product. And as a reading material, I will be very happy to provide you some reading material on, prepare some reading material on vector spaces and all that, inner product and all that we will give you. But for this course, I am not doing the general definition of a vector space and inner product and all that, because we have to move on. We have to see what is happening. We will do these things later. We have to more or less an idea that what's happening. So for us, it's enough to know what is a orthonormal basis in a two-dimensional vector space over complex numbers, what is an inner product, and what is a measurement, and move on. All right, so orthogonality I have done, orthonormal basis I have done. Now, this is the n-dimensional vector space over C. I will do these things. I can kind of do sometime later. An inner product in general, single qubit measurement, a general statement of whatever I have said. It is here. So this is what we have done. And now we will move on to something called an outer product. So we have talked about inner product and we will talk about outer product. Now, before going into the outer product, I would like to tell you about the transformations. Now the point is that I have told you that I have a qubit. Now I can create a qubit. I will show you how to create a qubit. Yes, I can create a qubit, but I can only measure it. I can only measure it. Okay, and so a qubit can be can take a state from a very large state space, but when I measure, it collapses to one of the measurement vectors with a certain kind of probability. Wonderful. Now, so I cannot know the exact state of the qubit, but what I can do is that I can create a qubit in a particular state, keep on creating many qubits and keep on measuring with a particular basis. And based on the sample, I may be able to say something. So suppose I have created KET0 and I keep on measuring it with KET0, KET1 thing, it will always give me KET0 result. So after some time, I will have reasonably, I can probably say, probably this vector is very close to KET0. So suppose, on the other hand, if I have got a vector KET0 plus KET1 divided by square root of 2, and I measure with respect to KET0, KET1, after a long time, I will see that half of the times, more or less half of the times, I am getting KET0, half of the times I am getting KET1, and then I will say that most probably this vector is an equal superposition of the two basis vectors KET0 and KET1. So I can do some kind of statistical analysis by using these things, and that is actually done. But what the theory says that we can do, we will also keep on doing this on our quantum machine, that I can transform the state vectors. So if I have, we can transform the quantum states, state vectors. by using unitary transformations. Now, what are unitary transformations? Let us not go into again details. So usually these are all linear transformations. So a linear transformation on a finite dimensional vector space is always a matrix. Now, why it is a matrix? That's linear algebra. I am not going to discuss that now. But when I'm talking about a transformation, it is a matrix. I will tell you the matrix. And if I have a matrix, it has to be invertible, and its inverse. If it's the inverse is the conjugate transpose, that is, if I take the conjugate of all the entries and transpose it, and if that becomes the inverse of the matrix, then I call that a unitary matrix. And what we know from the theory of quantum mechanics, that only transformations that are eligible to be transformations in this context are unitary transformations. Wonderful. So we will only do unitary transformations. Now, if you look at this transformation, what is this transformation? This matrix is 0, 1, 1, 0. If I take the conjugate transpose, so I take the conjugate of 1 is 1, so conjugate of 0 is 0, so I don't have to worry. And I take the transpose, so that also becomes this. And now 0, 1, 1, 0, dagger, this symbol is called dagger, and 0, 1, 1, 0, this is 0, 1, 1, 0, and 0, 1, 1, 0, this gives me 1, 0, 0, 1. So this is identity. So this is a unitary transformation. Now, if I apply this transformation over the quantum state psi, since psi is written as A ket 0 plus B ket 1, this also corresponds to the vector this matrix 2 by 1 matrix AB. So if I apply this, so 0, 1, 1, 0 over AB, so what do I get? So 0, A, 0, this is 1, 1 into B is B, 1 into A is A, and 0 into, so I get BA. So this BA corresponds to the state B ket 0 plus A ket 1. Therefore, I can say that if I call this transform X, this transform X times ket psi is equal to B ket 0 plus A ket 1. So this is the transformation. So this transformation flips the coefficients. These coefficients are called probability amplitudes. So this flips the coefficient. Now what happens if we use this transformation to over ket 0? So I know now that ket x psi gives me b times ket 0 plus a times ket 1, where ket psi is a times ket 0 plus b times ket 1. All right. Now the question is that suppose I have ket x times ket 0. Of course, then I am going to get ket 1. And if I get x times ket 1, then I am going to get ket 0. So see, its transformation is taking ket 0 to ket 1 and ket 1 to ket 0. So if I have a classical circuit and I am encoding 0 by ket 0 and 1 by ket 1 and mapping onto mapping into a quantum circuit like this and apply X, the X is working exactly like the NOT gate. So in a way, all right. So, so it is like this. The only thing that I have to now understand that what I am writing over here, what is this thing? So that thing can also be, this is called the inner product, outer product. Now, I would like to explain that. The outer product is defined over here. Instead of reading the definition, I will go here and tell you what is happening. So I will go to this slide, see. So what is the matrix corresponding to K0, X? This is 0, 1, 1, 0. Now see that I have got two vectors. One is K0, that is 1, 0. Another vector is K1, 0, 1. I can actually produce two more vectors, that is BRA0, that is 1, 0, and BRA1, which is 0, 1. Now see that I have seen that what is inner product, that is bracket. Now if we do get bra, then what happens? So suppose I start doing this. Suppose I first write get and then write get 0, bra 0. Then this is a vector matrix 0, 1. This is a 2 by 1 matrix, and this is a 1 by 2 matrix. And they do multiply this, and if I multiply, you see that I will get 1, 0, 0, 0. Now suppose I take get 0, bra 1, so then it is 1, 0 and 0, 1, and then see what will happen. This is 0 now, this is 1, this is 0 now, and this is 0. And again, if I take get 1, bra 0, then what will happen? What is get 1? That is 0, 1, and bra 0 is 1, 0. So what is this? This is 0, this is 0, this is 1, this is 0. And then again, if I've got get 1, bra 1, this is 0, 1, 0, 1, and see it will be 0, it will be 0, 0, and 1. So in fact, if you are careful, you will see that if I have a matrix A, B, C, and D, then I can write this matrix as A 1, 0, 0, 1 plus B 0, 1, 1, A 1, 0, 0, 0, B 0, 1, 0, 0, C 0, 0, 1, 0 plus D 0, 0, 0, 1. And this in turn I can write A get 0 bra 0 plus B get 0 bra 1 plus C get 1 bra 0 plus D get 1 bra 1. Now see, I've done all these things. Now, so if I have a matrix now, X is 0, 1, 1, 0. So B is 0 and C is 0. So therefore, X is get 0 bra 1 plus get 1 bra 0. Right, that is exactly what I have written here. If you see this thing. K0 bra1, K1 bra0. It's addition, so there is no problem. They can commute. So it is here. Okay. So this is the way to write these transformations, and these particular things here are called outer products. These are outer products. And what is how to do outer products? The rule is over here. That is exactly what I have shown. I have made I see that I have made a little bit of a mistake over here, and that is because I have not told you this, because when it doesn't matter here, because I am actually taking the conjugate. I am assuming that I am taking the conjugate. So when you are taking outer product in general, you have to be careful over here. So if you are doing this, be careful that you have to, this bra, this is conjugate, so you will get conjugate here, so exactly you will get this. So if you have so be careful there. I had only real coefficients, so I just worked without thinking of the conjugates. All right. So now I think we can have a short question answer. I mean, like, I will open the chat and answer your queries. Okay, Joydeep Ghodok. If I have understood correctly, if the qubits are in superposition, we measure, it will collapse. But if the qubits are already in K0 and K1 state, they are not going to, of course. I mean, if you are measuring with respect to K0 and K1, then if they are, not in superposition state, they will give you the correct result. And otherwise, yeah, they collapse to the same state, but you have to know a priori that it is in K0, K1. If you do not know, then you do not know. That is the point. But yes, of course. Sir, if this is Tonoy, if these measurements are probabilistic, then suppose for any calculation we want a bit K1, however we may or may not get K1, then we may get other possible results. And then yes, of course, I mean, like, so that is why the designing quantum algorithms is different from designing classical algorithms. Yes, and that's the point of this whole discussion. Joydeep Ghotok, if I have what, this is this is Anmol. What are qubits modeled after? How are they actually represented in a quantum computer? That I think Jyoti told yesterday, and he can tell you many more times. I mean, like, so there is no problem. Is X represented in slide 49 a measurement? No, it is a transformation. It's not a measurement. A measurement is not reversible. A measurement is irreversible. When you are doing a measurement, you are mapping to you are doing a projection. You cannot come back. But it is a transformation. You can apply X again and get back the original state. Okay, there is a in Bengali, there is one comment in Bengali from Devanjans. স্যার আপনি লাস্ট एक्स এর লাইনটা আর একবার বলবেন বুঝলাম না স্যার आप लास्ट एक्स का लाइन को और एक बार बताइए नहीं समझा तो ठीक है so Devanjan wants to understand how I wrote x. I will definitely do that. Physical realization of transformation are needed to reduce the physical circuits in the classical machines. Yeah, I mean, we will discuss all these things. Physical realization is a different issue altogether. We will go from here to see how we will represent the transformations in our simulator or the machine. once measured, can we use the same? I am not understanding it completely. Inner product helps in finding the probability of quantum state. Achha, this is from Shalini D. Inner product helps in finding the probability of quantum state of qubits. Outer product helps in transformations. Yeah, exactly. So inner product gives us that, finding the probability. That is exactly that is the point. Like if I have the measurement basis, I do the inner products. I mean, I know how the measurement the probabilities will be there. And if you have the outer product, it is a way to represent the transformations that are actually very. That is a very nice way of representing. Well, Qsim, it's a simulator, so it is neither photonics nor electron. I mean, like it's a simulator. So we will talk more about Qsim in the lectures and in our next lectures. Coming weeks. In the coming lectures, we will be talking more about that. Oh yeah, Pauli transformation, this X operation works on Z basis. Yeah, all those things are there, yeah. Why always we are considering unitary transformation? Yes, this is Varsha Tiwari. We are considering unitary transformation because we are only allowed by the theory of quantum mechanics to have unitary transformations. That is why. Rajasekhar has already said SAF and nothing else. Inner product, transformations does not help us in measurement, but transformations are transforming the states. So we'll keep on transforming the state, then measure and take some decision. Oh yeah, C and D are 0, 0, yeah. So I will do that. That's also Devanjan's question. So Shekhar Tyagi has said, learned a lot from this session. Thanks, sir. Thank you to you, and it's a great inspiration to me that we can exchange our ideas along this channel. Srinath LOT says that if the measurement is non-deterministic, how it will provide accurate result. I mean, that is the central question of what we are doing. So we will please be patient. We will be doing that in the coming lectures. Sir, your voice is breaking, so but I can do max that. I wish it is a offline class and then there it will be better. Yeah. Usman says measurement limitation is consequence of Heisenberg's uncertainty principle. That it is not so. Jyoti will explain later. Sir, Bishwajit Barik says C2 is what? C2 is the set of all ordered pairs of complex numbers. Like R2 is the set of all ordered pairs of real numbers. C2 is the set of all ordered pairs of complex numbers. So from the transform state, do we derive the original state theoretically? We don't have to. I mean, the original state, you can write the reverse transform and theoretically you can get it back. So these are all reversible. Nahida Majid Wani, please share the PPTs. Definitely, we will do that. Dr. Anand Kumar Singh, very informative lecture, sir. I am very happy, sir. I'm really very happy. All right, so I think we have more or less done a good deal of these things, and I need a little rest after this, but before taking the rest, proposed rest, I would like to do this X as I think Devanjan was telling. So how can I forget that? So the point is that, wait a moment. All right, so what he was telling that how to do this So single qubit measurement and all we are doing this, we were over here, all right. So we are over here, and he wants to know how X is written in that way, and rightly so, it's kind of, yeah. So see, the transformation X, okay, transformation X is essentially this 0, 1, 1, 0. Now in the outer product notation, we know what have we seen? It's bra 0, K 0 is 1, 0, 0, 1. Bra 0, K 1. Oh, I'm sorry, it is not 1, 0, 1, 0, 0, 0. 1, 0, 0, 1, 0, 0, 0. And this is 0, 1, 0, 0. Then K 0, bra 0. K 1, bra 0. That is 0, 0, 1, 0. And I should put a comma here, should a comma here, put a comma here, and get 1, bra 1, that gives me 0, 0, 0, 1. Now tell me, can I not write this as 0, 1, 0, 0 plus 0, 0, 1, 0? Of course I can write this. And then what is this? This is get 0, bra 1, and this is get 1, bra 0. All right, so I think now this should be clear. So this is how we write that. And now I will move back and go to this slide here. We'll see that I have, so identity can be written in this way. And I have told you that X can be written in this way. Now see Y, there are two other transforms, Y and Z. They also can be written in the same way. So please look at this and check that. Let us give some 5 minutes break because we have been kind of talking for about 1 hour. And after, so okay, and Jyoti in between will say something, and I'll just take 5 minutes break and then come back and we will go to the simulator. This time not the Qsim simulator, but I'll go to the IBM Qiskit simulator and show you the effect of these gates on the qubits. So, all right, will you come here and say, or here? Yes. Okay, so I'll kind of wait a moment. But I have to keep on sharing. I have just.
Yeah, hello. Good morning to everyone. I hope you guys can hear me. Yeah, cool. So we are in a break right now. So people who want to, I don't know, go stretch your leg or take a break, you are welcome to take a break. Just some minor announcements, nothing important. So first thing about this. So Sandeep Kumar Singh has asked, where have I shared the slides of yesterday? We have not shared the slides of yesterday yet. After today's session, they will be uploaded to the GitHub repo. And whenever any new upload has taken place, you will get email notifications for them. So do not worry. As soon as there is any upload, it will be you'll receive the notifications immediately. Regarding this course, as you might have noticed, the lecture format for this course is interactive and it happens in real time. So this is like, somewhat unlike the courses that you would encounter in NPTEL or, other paid platforms like Coursera or things like that, where you have pre-recorded lectures and, you're supposed to listen to them and you can maybe ask questions, maybe not ask questions. And, eventually there is an exam and there is a certification. So this course is not like that. Our aim here is essentially to have a real-time interaction as much as we can, to the extent that we can, with the attendees, and have an interaction where we can share some basic concepts and notions of quantum computing so that the people who are listening can understand the basics, the very basics. So this is not intended to be an advanced course, or technically it is not meant to be a course in a very serious sense. The aim of this course is to introduce a general audience and people who are not familiar with quantum mechanics, or even people who are not in the domain of quantum computing, to this area, because it is kind of an emerging area and a lot of work is being done here. So it will be there seems to be a lot of interest, and the market seems to be wanting more and more people who are capable of working in this field. So we are sharing it with you guys. Because of that, okay, so in between, so Sridhar Shivkumar has asked, please provide recordings. Miss Vandana or someone, are these sessions not being recorded? Are they just being streamed live? Can anyone answer from CTAC? Okay, yeah. So regarding the recordings, I'll get back to you. Okay, so what other? Okay, YouTube Live is already gets recorded, right? Cool, fine. So yeah, just go back to the stream links and see the things. So yeah, as I was mentioning, this course is meant to be an interactive course, so things will happen in a back and forth manner. So the progress of this course will be slightly chaotic. It will not be very organized. So kindly keep that in mind and bear with us. The reason for this course being relatively disorganized is because we are instructing and interacting with you in real time. So that is always going to be, there are going to be some, disruptions when we attempt to do that. We felt that sharing pre-recorded lectures and, keeping the whole thing very strict and rigorous and standardized kind of, takes the life out of it. So that is why we prefer doing live courses. Even though it's not offline in person, we'd like to have it online where we have real-time interactions with the students. So yeah, Sridhar, the YouTube live stream links, it is recorded. So the link has been shared for every session with you guys. So you can just go view the live stream, and there this entire session will be recorded. The GitHub URL, you'll be receiving it as soon as we start uploading things to it. Right now, nothing has been uploaded. That's why we have not shared the links for the GitHub repo. About the Qsim software, well, Qsim is, yes, of course, it's software, but technically you will just be accessing the computers that have Qsim running on them. So it is essentially, you'll be accessing Qsim over the web. I don't think you have to install Qsim locally. So in that sense, Qsim, we shall deal with it next week. So for Qsim account and Qsim access and all of these things, next week onwards, we shall be dealing with that. Yeah, Biswajit, I see that you've been asking where is the use for qubit. Well, you'll know eventually. Like, it's not a question I can answer in 1 or 2 words. The use of qubits and all of that is kind of the entire point of this course. So stick with us for 4 weeks and you will know what happens, what is the use for a qubit. Other than that, assignments, Kameshwari has asked. you'll get the assignments soon enough. Don't worry. When we give you assignments, we will give you enough time to solve them. When they come, they will come. And again, as soon as there is an assignment, everybody will get the announcement. It will never be the case that an assignment is released and it has not been announced. Certificate will be provided. Yes, a certificate will be provided, but the conditions for that we'll see later. Do you need laptops with Python installed? Yes, you will need laptops with Python installed. I mean, laptops, desktops, whatever. Yeah, right now we have not uploaded any PPTs, so you will not be able to get any PPTs. As I said, I shall be uploading today. So please, I mean, bear with us. Manoj Kanani has asked, any premier institute is working on building quantum supercomputer on the hardware side? Yeah, there are several. I mean, there are groups in virtually every IIT at this point. There are many groups in several of the ICERs. There are prominent groups in TIFR, IISc. So pretty much every premier institute in India is working on quantum computing at one level or the other. All you have to do is go to the respective institute websites, go to the, I don't know, electrical engineering, physics department, see what people are working on, or a Google search should tell you who's doing what. This is a serious course. I didn't mean to say this is not a serious course. What I'm trying to say is this is not an NPTEL course which can be substituted for a 4-credit course in your university. In that sense, this is not a stringent course like that. The material we are sharing here is very serious, and we try to be as precise as possible. I mean, we try to be not as precise as possible. We try to be achieve the maximum level of precision and accuracy when we are talking about the concepts. The point, however, is we do not have a preset syllabus that we are hell-bent upon covering. It's not like, we'll keep rushing over the topics just to cover a syllabus. Our aim here is to make sure maximum number of people understand whatever we are discussing. So be it even the very basics or some algorithms or some, further nuances of quantum computing, whatever we are discussing, our aim is to ensure that most of you get the message. Biswajit, I've answered the question about the certificate. I would also request that you stop reposting that question again and again. Where can you get the notes for the session? The notes will be uploaded soon. Once they are uploaded, you will find out. Yes, Neha has asked for an offline closing session. I don't think we can afford to invite, I mean, even if it's just the online attendees for this WebEx meeting, I don't think we can honestly afford to invite 520 people from all over the nation and conduct an offline session. I'm sorry, it's beyond our capabilities currently. Maybe later, maybe in the near future, we can see if we can have an offline session where people from all over the nation are can be invited. But right now, yeah, I'm sorry. Yeah, we would love to invite, as a large number of people and hold an open course for everyone. But right now, we don't have the infrastructure or the resources to do that. Maybe after seeing courses like this, the powers that be may grant us the necessary resources to realize your request. I sometimes say guys, but it's a general address, my friend. Like, I mean, in this course, so where is this message? Is it further down? Yeah, sure. Now I'm handing control over to Professor Gangopadhyay. We can resume the session.
Okay. So, all right, we'll come back, and I will stop sharing this thing. Stop sharing this, and I will share something else. Actually, take this out. Share this. So, sign out. Whatever. Yeah. So now I will share my another screen, and that's Yes. So if you happen to see the Qiskit thing, right, of this IBM Qiskit portal, it is possible you will arrive here. This is quantumcomputing.ibm.com, and you will arrive here and you can prepare a sign in. You can sign in. So I will use my credentials now. Yes, so I'm logging in there. All right, and I am launching a lab. Yeah, it works. And I will show you some programs that I have, small programs that I have written, and then to kind of manipulate them and see that whether we are in a position to see what is happening. So these are gates and some simple circuits. I think you are probably there, it is visible. So let us make it larger. Yeah. All right, so we are here. So it's a Python-like thing. So it's like this, that first you have to, when you write, you have to import Qiskit and call it Q for, if you like, you can call it Q, and we can start, construct, simulate, and run, simulate, run circuits. Simulate and run quantum circuits. So you have to first import Qiskit and let us call it Q. Then import NumPy, as usual, call it NP. And then you can kind of go here. Let us see the comments. At least we should be able to read all the comments. And import matplot library Python plot as PLT, and also for graph. So we will be doing this. So let us run it. All right. Now, how Qiskit is used? So quantum circuit is a class in Qiskit's way of designing a quantum circuit. It takes two inputs, Q bits and classical bits, which tell the circuit how many Q bits and how many classical bits to use. All right. So I have to build a circuit. So I am saying that this is the circuit and it is equal to, this is the quantum circuit class. And I have to specify how many qubits and how many there is a how many qubits and how many circuits we have to specify. So we will specify. Now we are creating a very simple circuit. So see Q dot. So Q dot means what is Q? Q is Qiskit. Now within Qiskit you have the class quantum circuit, and you are specifying by 1 1. So that means you are asking for one quantum bit and one classical bit, and this whole thing goes into this circuit. So let us run this, the shift thing, and then I have a this for drawing quantum circuit. So I have a Qiskit has a function circ.draw output m equal to mpl for drawing diagrams or circuits. So sometimes it's a pictorial diagram, and that's very nice. We would like to see how the circuit works and how it looks like. So now see the drawing quantum circuits to make sure the image displayed in our can be used for display function. So I am again running this, and after this is for drawing. So what I am doing, I'm drawing this circuit. What happens? Yes, you see what I wrote here. I specified a circuit, and it is q dot quantum circuit 1 and then I display circuit dot draw. So I am, for whatever circuit I have created, I want to draw it. So this circuit now is only showing 1q. So it's a one quantum bit, that's q, and then another, this is a 0th quantum bit, you will see later, and another classical bit. So classical bit goes in the two lines. Why two lines? That means it is 0 1. One bit means two states, and quantum bits, it can be of any state. But as a default, it is always at 0. All right. Now, so now I have told this X gate. Now we will see what happens if I use X gate. So adding a NOT gate, aka an X gate to the qubit 0. So when I am doing this, the 0th qubit, what is the 0th qubit? It is 0, and by default, it is at 0. So if I add this NOT gate, so I am applying circuit.x, that is the X gate on this, on the 0th thing, and then what happens? Now I'm drawing the circuit. See, I have drawn the circuit over here, and then what does the X gate do? This is just before this I did the theory. So this is the matrix corresponding to X gate, and this circuit.x, so this invokes the X gate, and whatever you put in the argument. Oh, why do we have to? We will see this by classical thing. Okay. So if you apply this, then you will see that this is the target qubit. So here the target qubit is 0th qubit, and which is the 0th qubit? This is the 0th qubit, and on the target qubit I am applying the X gate, and then circ is initialized with quantum circuit, and target is the number of qubits that you use. So these things are given. And then we will have this. All right, so I have got this. So see. I have this. I have applied the X gate. This is a new circuit. This is for circuit X. Quantum this is only for the X gate. And so I have done this. Now the point is that I will not go for the Y gates and all that. I will now come down, and this is what we had. Now I will show that how to measure, right? So let us come down. All right, so I would like to come even down. So here. Here. I will keep on modifying this. So here you see I am using one circuit, this, and then let us do something like this. I will Okay, so I will, let us make it okay, let it be like this, no problem. And then what I do is that instead of this, I will comment it out. So my circuit is circuit H, doesn't matter. Now I am applying X gate over this. So let us see what happens over here. See, it is changed. Now suppose I open up this also again, what will happen? You see, I have put a H gate and then an X gate, but I don't want this to happen. So I will first do this. All right. What is this? This is X gate. And now you were wondering that why I am using this. This is where measurement comes in. So I want to measure the first qubit and store it as a measurement result to the second qubit. So this is two hidden cells are there. So is there anything there? No. Okay. So see, this is again a command. So what does it say? That circuit H is now this. Now it says that measure with respect to the standard basis. With respect to the standard basis, measure this 0th qubit, that is this qubit. It is in the default, it is set to get 0, and then throw the store the measurement result. This classical thing. Now what happens in the classical thing? It can store either 0 or 1. So this now explains the question that why we need a classical qubit, sorry, a classical bit in a quantum circuit. We need a classical bit in a quantum circuit, because if we measure, where will we store the measurement result? For storing the measurement result, suppose I have got I have a gate 0. I have done something with it. After that I am measuring. Now where will I store the result? The result will be stored on a classical bit. This is exactly what we have done. So I am measuring this, storing here. After I have done this, now we have to look at the back end, and that is where we will be working on when we are working on the Qsim, because here we are putting the QASM simulator, the IBM simulator here. We will replace this by our Qsim simulator, and we will see the extra features there and other things. That's a different simulator. So we will see this. Now we give a job and we take many shots. It's not only once, we take many shots. And now let us see what happens. If I run it, see, the result is 1. This is 1. So that means it was 0. It was 0. It is by default 0. I do X. Now what do I get? I get 1. Now suppose I do X 2 times, then what will happen? All right. I get 2 times. Here I am doing this. See, the circuit changes. And now this is where I am submitting the job, q.execute, this to the backend. Backend is QASM simulator. As I told you, we will use a different backend when we are doing the Qsim, of course. This is a different backend. And shots, these many shots, because as you know, this is a kind of probabilistic. All right, now see. And then it does the counting, and then it produces the histogram and display. So now if I do this, what is the result? See, it is 0. This is always 0. So 0 2 times. 2 times not, it is 0. If you want to do another time, Now see, I am extending this. Now I am adding the measurement, and you see predictably what is happening. It is again 1. So it is flipping all right. Now the point is that suppose I want to see something different. So here what's happening is I am using these X gates over here. Now I've got another gate which is called the Hadamard gate, which I will describe later. So this is a gate that does something else. So let me actually, I will show you the results. So I think I will go to my lecture slide, show you this, then you will understand what's happening, and then I will be able to tell you more. All right, so let me stop sharing this and go to my slides again. All right, so I have done this. So these things we can always do, so that's not a problem. What is more, in some ways, more interesting is this one, the Hadamard transform. This is also a, okay, let me share the slides. All right, so welcome back to the slides again. See, this is another transformation. So what transformation is it? So let me write down. So this is called the Hadamard transform. So the matrix corresponding to this transformation is this. Now, if I measure this, if I apply this on a qubit, the question is what will happen. Now, I can actually use this bracket notation to make it easy to kind of make it. I mean, because this notation we will be using. So suppose I have got K0. So that is Q. Remember that I was saying in that simulator, I was writing Q. Q is a quantum bit. And there is a classical bit. We saw that. It is one classical, one quantum. And this Q is set to K0. Now this is a transformation. The matrix form of this transformation is this. And if you patiently go through the previous slides, what I have done, you will see that that can be written in this way. This is the way of writing. This is K0 bra 0 plus K1 bra 1 plus K0 bra 1 minus K1 bra 1. You can do that, and then if you do this, you will get a unitary transformation like this. Now, suppose I'm applying H over this, then how should it look like? I could have done the matrix multiplication and quickly got you the result, but I want to show you how we work with this bracket notation. So H is replaced by 1 by square root of 2, K0 bra 1, sorry, K0 bra 0 plus K1 bra 0 plus K0 bra 1 minus K1 bra 1, and here I will get K0. And then, so what will happen? See, these are matrices. So when you are working with this bracket and all these things, if you get confused at what to do, they will follow all the rules of matrix multiplication. They are all matrices. So you have a bunch of sums of some matrices over here and another matrix over here. Therefore, no one can stop us from doing this. So I have got K0, and see, this is K0, this is bra 0, and this is K0. We know that when these two matrices combine, they become bracket. So I can write bra 0, this is bra 0, K0. Then see, it is K1 bra 0, and it will combine with, have I made any mistake? No, it's all right. combined with this, you will get this. Then you have ket 0 pra1 combining with ket 0, so bracket 1 0 minus ket 1 pra1 combining with this bracket 1 0. Now this basis is orthonormal. Therefore, I can, from whatever we know, this is 1 and this is 1, but this is 0 and this is 0. All right. And therefore, I'll come over here and write this. This is 1. So it is ket 0 plus this is 1, ket 1. So my change state is ket 0 pi square root of 2, and we usually write like this. So the state that I get is this one, ket 0 plus ket 1 divided by square root of 2. Now, if you measure this state with respect to standard basis, what will happen? So suppose your measurement basis is this, ket 0 comma ket 1. Sorry. Suppose your measurement basis is this. So if I want to know what is the probability that I will get ket 0, I have to take pra 0 and take inner product this. This inner product is bracket 0 0 square root 2 plus bracket 0 1 square root 2. Bracket 0 1 is 0 and bracket 0 0 is 1, so 1 by square root of 2. And if I want to know what is the projection in the direction of ket 1, so it is pra 1 ket 0 plus ket 1 divided by square root 2. So this is going to be 1 0 square root 2 plus 1 1 square root 2. So the probability corresponding to this is half, because 1 by square root 2 whole square is half, and this is also half. So that means that more or less equal number of times, if you are measuring the effect of H on this state, effect of H on the ket 0 state, whatever state you will have, and after that if you measure with respect to the standard basis, that is ket 0, ket 1, so your measurement result should be equal to ket 0 and ket 1 each, more or less half of the times each. That's you are going to get. The question is, if I build this circuit on the quantum machine, am I going to, or a simulator, am I going to get that? So that is what we are going to see presently. And so I stop sharing this one and go back and share the other slide, the other window, which is this one. All right, here we are back here again. All right, see what I have done over here. So I am using QSM simulator of IBM, and I have prepared this circuit. This is my Q, and I know that Q is set to ket 0. I am applying this, so I know the result I have shown you just a while back. And then I am going to see how the circuit looks like with the measurement. The measurement is this. I am going to measure, and my backend is QSM simulator, and I am going to do this. When I measure C, this is what I am getting. This is so nice to see this. So 0 I am getting, so I have given 1024 many shots, so I am doing that, and like 515 times I am getting 0 and 509 times I am getting 1 output on the classical register. So if I do it again, I can do it again and again because it's a simulator. See, 511, 513. It is not mathematics. It is sending the job to a simulator which is simulating a quantum machine. And see, it is like this. Yeah. So that is what's happening here. That is what I wanted to show you. And suppose that I do something else, I put another Hadamard, then what will happen? Since Hadamard is inverse of itself, if I put another Hadamard, so I've got this circuit, put the measurement here, I've got this circuit, and then I do this. What do I get? All the time, deterministically, it is get 0. So see, that is what should be happening. I can predict what will happen. All right, so that is what we have. We remove this Hadamard because it's very obvious, and I'll remove this. I'll put this over here and show you this here, and then run it again here, and like this. So I cut this time, we got much less number of 1 than 0. So yes, it is not a real quantum computer, but it is a simulation of a quantum computer. Now, what we are going to do in QSM, that is QSM. It is a simulator of a simulator. Now we have Qsim, but Qsim does something more that IBM did later. IBM now does that also. That see, when you are applying these gates, there are some gate errors. In the Qsim, you can simulate that error also and then get more realistic results. So that is what we have. So I think that this is the time to stop because it's 11:30. Stop. And let us have some questions now. Let us have some questions, and then we will discuss what to do. Okay. Chat. Yes, so now the questions are coming in. So many questions. So I'm so happy to see these so many questions. I think I should stop sharing now and answer questions because I can see myself. I can see the chat channel. Yeah. Taking the last question, is Qiskit classical simulator or of a quantum computation, or is quantum computation package? I mean, it's a simulator in a classical machine, but within that you can actually access the actual machine. What is the measurement? What is the physical significance of matrix inverse? And it is a inverse transform. how is the measurement which is a qubit is stored in class? How measurement which is qubit is measurement result gives you two alternatives, right? So when you measure, you are getting either, let us say, ket0 or ket1. Then you can do a kind of encoding. 0 you can store as 0, 1 you can store as 1. So that is why it is essentially equivalent to classical information, because you have got two alternatives. Yeah, Dr. Punofji, yeah, of course. I mean, like, yeah. Hadamard is used to give equal probability to all states when we start working with qubit, I think. Yes, yes, exactly. Ankita Jaswal, I mean, that's exactly the thing. Hadamard kind of gives all the, I mean, they in equal superposition state, and that's very important that we will come to see in upcoming lectures. And now this example run on simulator, it is run on simulator. How can we access IBM actual machine? I think IBM allows free access to the actual machine also. So you have to check the options in the IBM portal, on the IBM portal. So then Orunabho Das, as X gate analogous and not gate, yes, what is the Hadamard gate analogous? So Hadamard gate doesn't have any analogous gate. I mean, it's very much, it has a superposition. I mean, X gate is, you can have something like not gate there. But for Hadamard gate, it's really interesting because some people say that you are really doing something quantum if you have two things. One is superposition, the other is entanglement. We have not talked about entanglement yet. We will talk about entanglement the next week. But we are talking about superposition. So we are seeing that there is a very interesting effect of the Hadamard gate. So I apply Hadamard gate on gate 0, and I get equal superposition of 0 and 1. So if you want to remember today's lecture, remember only this, that I have created superposition from a state which is in the superposition of two basis states starting from a basis state. No, I am showing probability half because, well, this is Orunabhu was there, then, I am losing track, like, yeah, that was Sahil. Sahil said something in that Hadamard gate single one gave both 0 and 1, but when you added one more, it gave only one single. Yeah, Sahil. So the reason is that, see, what happens that Hadamard is self-inverse. So you apply Hadamard, you get equal superposition. On that, you apply Hadamard again, you again get back the original state. Yes, that's what's happening. So I actually showed stepwise how to write the code. We will give you a demonstration code so that you can write on your machine. Hadamard gate single one gave 0 and 1. Okay, that's over. Hadamard gate computational explanation was very wonderful, sir. Thank you. Madhuri Konnur, thank you very much for your comments. I also find this very interesting because here I'm kind of going from, it's almost for me going from classical to quantum. I had one gate, you have something, gate 0, gate 1, I apply a gate, it is becoming equal superposition. I apply it again, I get back again whatever was before. I find it very interesting. Mohadev Mondol, sir, which program we need for this simulation? I showed the program. Sir, what is the significance of Pauli transformation? We will gradually tell you, we have shown you the Pauli transformations. What is the use of Hadamard gate? Of course, I mean, like, we'll show what is the use of Hadamard gate. Can you explain relevance of Hadamard gate? Of course, I will do that, but that's next week. Please explain double Hadamard gate. Double Hadamard gate is identity. If you take, I am telling you, if you take 1 by square root of 2, I've given that. Give that. So if you take 1 by square root 2, 1, 1, 1 minus 1, and 1 by square root 2, 1, 1, 1 minus 1, if you just make the matrix multiplication, you will get identity matrix. And that is what we are seeing on the quantum computer, our simulator. But the question is that if these Hadamard gates have some errors, gate errors, then what will happen? That could be interesting. That we will see on our Qsim simulator. If the initial state of a quantum circuit is 0, how can we set it to one state? If initial state is 0, to state it to just apply X gate, it will switch 0 to 1, gate 0 to gate 1. Majid Shabir, is Qiskit classical simulator? This I have actually done. What is a physics? Oh, this I have done. I have gone upstairs, I think. If we finally use classical gate to store information from quantum, we are getting only 0, 1. We can get more amount from a quantum comp. How can we get? Ayush Sharma, this is a very interesting question. If we finally use classical gate to store information from quantum gate, we are getting only 1 or 0 as a result. How can we get more amount of information from a quantum computer? This is the central question, and this is what we are going to answer, but that is next week. And this is the central question that is I am asking myself. But we will answer this next week. We cannot do everything in 1 week. Tanoy, they asked the calculations in simulator is really happens in quantum computer. Simulator is simulator, but it is simulating a quantum computer. Srinivas asked that how many classical bits are required to store one quantum bit? You cannot store a quantum bit qubit in a classical thing, right? Can you? In general, no. I mean, like, okay. So let's go down. Kapil Varma says that guide us more on writing code on simulator that can be used to answer questions. Exactly, so that is why this course is happening. I mean, that's what we would like to explore, that how to write codes. We will see more on these things. So here, this also what Kapil is saying. This is also something that is my point. Like our point here is to write codes and see whatever is happening. So whatever we are learning to so that we can design algorithms, write codes and all that. So we have got physicists are telling us something, engineers are telling us something. So all these things we have accumulated inside our brain, and our goal is to at least start learning how to design quantum algorithms, how to write codes. Yeah, so that's what we are here for. So come down, classical results. Okay, Surajit Bosu is writing in Bangla, so I will read it in Bangla. And by the way, I think you can here ask questions in how many languages? Bangla, Hindi, Tamil, Telugu also maybe. Bangla, Hindi, Tamil, Telugu, then French and English. You can Russian also. You can actually write anything. I will do Google Translate and answer. I will cut paste Google Translate answer. All right, so no problem. So okay, so anyway, So classical results, what Surajit says is classical results are deterministic, but qubit measurement is probabilistic. Then how then we will do anything there? Yes, that is the question. We will answer these questions. Yes. Actually, see, this sense of wonder is most important. All right. So why it is important? Because that is my point. Like people are saying that this will be commercially very nice, and many other things are commercially very nice. But this sense of wonder is that like I mean, you have a machine which is a very restricted machine and very expensive machine. Now, how are we going to exploit that? Why people are saying that we are going to exploit that? So that is what we are going to learn. What happens if we use bases containing complex numbers? We have to work according to the rules and we will get the same answers. Kapil Verma, thank you, sir, for answering. Thank you very much about writing code on simulator for QC. Yeah. Which Python package and all, please, ask someone. Sir, can we mix quantum with classical to stabilize the information? I know, I am kind of, so quickly I cannot tell this. Why do we use classical resident concept? Sir, what is the difference between Hadamard gate and Pauli transform, all these things? I think now we can stop here. More or less, I have answered the question. Acha, Hilal is saying that when are you going to show examples on Qsim next week? I will show Qsim next week. We know that there are some algorithms where quantum computer is very fast on the classical computers, but is this true for all algorithms? It is not true for all algorithms. I can show you algorithms where quantum computers are not helpful at all. So it's no. Please explain code part again using gate, any gate. So see, the code part I have given a demo, but I am talking only for around more than 2 hours. So I will hand it over. We will take a short break and hand it over to my student Jyoti. And and we will meet again next week. And then I will do.
Still have a session.
No, not now. Jyoti will talk about this. Jyoti will talk, and then after that, next week again we will meet, and then we will do more coding and many things that we have learned this week. And in between, we will post material that for you so that you can go through these things and like that. All right. So yeah, Manas Sahu, thank you very much. Thank you. I am really very happy if whatever I am saying is helpful and all. I have got another comment, and I am teaching this course at university level for past 2 years, but every time learning same topics from different professors, getting different perspectives, such a beautiful and ever exciting domain. Thanks a whole. Thank you very much. Thank you very much. I mean, so I mean, that is also my point. Like many of us are teaching this course in different places, and this kind of it's nice if we share our experience and way we are explaining things and all that. So as I would also like to hear how you are teaching at your place. So thank you very much. All right, so let me stop here, and Jyoti will take over in 10 minutes time. Please give us a little break. Okay, I mean, please let us have a little break. Oh no, so okay. So all right.
Yes, now that the time now is 11:43. So we shall reconvene at 11:55. I hope everyone got the message. We shall reconvene at 11:55. So please take a break. Yeah. So, am I audible now? The speaker is speaking now. So, yeah, thank you. So, yes, we shall begin our session today. So, yeah, before I start with my presentation, I'd like to talk about one or two things regarding the contents of this course. Now, of course, I'm sure we have a varied audience. We have students, teachers. We probably even have people from the non-academic sphere who have joined us for this course. It is a great and wonderful thing that we have such a varied audience for this course. So some of you might have the question as to why are we learning physics and linear algebra and matrix multiplication and all of this for what is essentially a computation course. So for that, I would like to say, I'd like to take an example. Say if someone was trying to learn computer programming, like classical computation, computer science as we know it today, if someone was trying to write a computer program, say 50 years ago in 1973, then the methods they would have used and the modes they would have used to write the program were drastically different from what we do these days. Like in 1973, I think the C programming language was only 2 years old. And it was implemented as an assembly language program. So it wasn't even a high level language. So it was essentially implemented in terms of assembly languages, and the programs were stored on tape-based memory. There were no hard drives, there were no solid-state drives, and many of those computers actually had an output which was in the form of a printer. They didn't even have displays, and very few of those computers had keyboards. So in many of those cases, those programs had to be fed in terms of punch tapes or punch cards. So some of you might know what these words that I am talking mean. These days, however, if you would like to write a program in a certain language to do a certain process, you can open something like ChatGPT and write the description of your program in your language. In fact, you can write it in any language, and the AI will read the language, interpret what you have written, and based on whatever learning it has done, it will generate the program automatically. So that is where we stand today. Similarly, quantum computing as an area is in its very beginnings. That is why courses that discuss the concepts of quantum computing are discussing the very basics of the subject itself. It is because of the fact that quantum computing as a subject, as a discipline, as a paradigm of computation is still in its very initial stage. That is essentially the reason why we are covering the aspects of physics in our course. Now 15 years hence, when I mean if and when this subject becomes a standard, and quantum computers, their implementation, their architecture, and our modes of interacting, like input output and all of these things, once they have been standardized, then of course people who are learning quantum computing at that point, at that time, at that day and age, need not study the physics. They can ignore all of these things, because every subsequent layer has been standardized and the interaction between them has been formalized to a certain extent. Right now, the reason why we are teaching math, apologies, I muted myself accidentally. Okay, so yeah, just 1 second, please. Uh, yeah, just 1 second. There seems to have been a power outage. Yeah. Yes. Yeah, apologies for the interruption. We had a power outage here, so I had to move things around. I hope there will be no further interruptions. I'd like to take. Yeah, I'm back. So yeah, apologies for the interruption. So now I will. To conclude what I was saying before, the reason why we are talking about the basics is because the only thing we know are the basics. The advanced stuff we do not know yet. That is the straightforward, simple reason. Like people might have different interpretations for what will eventually become quantum computing, but right now there are no standard versions available. That is precisely the reason why we are learning what to say, like quantum mechanics. We are talking about linear superposition. We are talking about entanglement and all these things. Of course, even when we move to an advanced level, we shall be referring to these things, but learning what is exactly happening inside each and every one of those devices will not be necessary. For instances, when we are working on our modern day laptop today, not every one of us knows about FinFET technologies used for the manufacturing of the transistors on a laptop computer. So that is kind of the reason why we do not discuss about the basics of the computer itself in order to perform computation. But right now, the only knowledge we have is the basics. So that is all we can discuss. So with that, I will begin my presentation for today. Yeah, I hope my slides are visible. Yeah, thank you for confirming that. So today we shall be talking essentially about single qubit states and their visualization. Now, Professor Gangopadhyay in his lectures has now moved on to quantum transformations and quantum gates, and you're seeing what is happening in the simulator. My aim in today's discussion is to formalize the mathematics that is used to describe single qubit states. Again, give reinforce it with some physical context, and kind of bridge the gap. So the next time you see a quantum circuit that is being implemented by IBM Q or Qsim or something, you will know exactly what is happening. So as always, during this session, I will be unable to focus on your chat. So whatever questions you have, I humbly request you to post them at the end of the session, because whatever you post now, I will not be able to see it, and there will be a huge backlog of messages, which will be impractical for me to kind of rush through. So whatever questions you have, kindly hold on to them. I shall address them as soon as I'm done with today's session. So moving on. This is again the overview of the topics. So first and foremost, what do we know so far? So we know that in quantum computing, the most fundamental unit of information is a quantum bit, which is also called a qubit. And a qubit, as we have seen so far, is represented as a vector. It is a mathematical object. A qubit is a mathematical object. Now, this statement is important. A qubit can be used to represent the physical state. Yeah, I should have used the word physical here. When I upload the slides, I shall add it. A a qubit is used to represent the physical state of many objects. So as an example, in yesterday's discussion, in my part of yesterday's session, we considered photons where the qubit was used to represent the polarization state of the photon. Now, what do I mean by this? The vertical polarization, the electromagnetic wave corresponding to the vertical polarization was represented by Ket0, and the electromagnetic wave corresponding to the horizontal polarization was represented by Ket1. Now, this was an assignment that I made on the spot. There is no logic here. I'm just assigning them. I could have also assigned arbitrarily, I could have made vertical as Ket1 and horizontal as Ket0. I could have given any symbol here. Just for the sake of a notational consistency, I am choosing to call this Ket0 and I'm choosing to call horizontal polarization as Ket1. And we also saw this, that a real superposition. So whenever I'm using the word superposition, all you have to understand is that in the context of vectors, it is a linear combination. So if I have two vectors v1, v2, any linear combination a times v1 plus b times v2 is called a superposition. So a real superposition, that is where these a and b, these two numbers are real numbers. A real superposition, linear combination of Ket0 and Ket1 formed what were called oblique polarization states. So these were states where the electromagnetic wave kind of oscillated in a plane that was oriented obliquely with respect to the vertical and horizontal axis. And towards the end, I mentioned that complex superposition expands this and also accounts for circular and elliptical polarization states. So these are typically all, I mean, not typically, when we are considering light waves propagating through free space, these are all the polarization states that can exist. It can be plane polarized, it can be circularly polarized, it can be elliptically polarized. And all of these polarization states can be represented by real and complex linear combinations of Ket0 and Ket1. Remember, Ket0 represents the vertical polarization and Ket1 represents the horizontal polarization. So I can choose any two combinations. As I mentioned yesterday, I can choose any two combinations of other orthogonal states as well. Now, why am I using orthogonal states? There is a bit of linear algebra in there. We are not going into that right now. And that is also technically not necessary for understanding the ins and outs of quantum computing. However, at a later date, if more clarification in linear algebra is needed, I'll share some materials with respect to that. But for this course, that is not required. All you need to understand is that if you have a pair of orthogonal states, then they can be used to form a basis. And any basis, as Sir mentioned earlier in the session today, their linear combination can be used to represent every vector in that space. That is the definition of a basis. Therefore, since these two polarization states form the basis, their linear combinations will represent all possible physical polarization states. That is understood. Now we come to the concept of measurement. What is measurement? As we saw yesterday in both the video and in my explanation, we can have a polarizer, a kind of a film, an object that is aligned in a certain direction. So right now I'm choosing that direction to be a vertically aligned polarizer. So this is, if you remember yesterday what was seen in the video, this is a polarizer where the arrow was pointing kind of upwards, vertically. So a vertically aligned polarizer can be used to measure the polarization state of these photons. The polarization state is represented by the qubit. Now, if a photon passes through this polarizer, like if a photon that is coming incident on one side of this polarizer, if it is emerging out of the other side, then the polarization is said to be measured as vertically aligned. If a photon comes out of this polarizer, then the measurement outcome is a vertically aligned photon. If a photon is blocked, if it is absorbed by the same polarizer, then its polarization is measured to be horizontally aligned. So this is important. Measuring a qubit state with respect to a basis will change the quantum state of a photon. And this is true for any physical object. In this case, we considered a photon, so I'm talking about a photon, but in general, any quantum measurement will change the state of that object in general. So, and more importantly, if we are measuring with respect to a certain basis, in this case, I would like to remind you and reiterate that the bases we have chosen are the vertical and horizontal polarizations, which are represented by Ket0 and Ket1. Now, if I'm measuring with respect to this basis, Ket0 and Ket1, then the outcome will only be either of these basis elements. It will either be Ket0 or be Ket1. Now, the last two statements in these slides, the first one is okay, I will just read it out. The outcome of a quantum measurement in general is represented by a real number. Now, why is this so? The reason is because this is how the theory of quantum mechanics was developed. Measurements are supposed to correspond to physical quantities, and physical quantities have real values. So this is the basic assertion on which the theory was built, and therefore the outcome of a quantum measurement is always going to be represented by a real number. In the case of a quantum bit, in the case of a qubit, the measurement outcome can be represented by a single classical bit. This is why when Professor Gangopadhyay showed you the classical circuit, he had a quantum bit Q and a classical bit C. And whenever a measurement was done, you saw that the measurement symbol had an arrow moving from the qubit to the classical bit. This implies that the measurement outcome from the quantum bit, from the qubit, is migrating and is being stored in the classical bit. So the measurement outcome is always a real number. In the case of a single qubit, the measurement outcome is a single classical bit. So now we shall come to the mathematics. This is the recap is done. So as we have been seeing since yesterday, we are concerned as far as single qubits go, we are concerned with the vector space C2 that is represented by, a vector in this space can be represented by ket psi. This is a Greek alphabet as a column vector A comma B, where A and B are both complex numbers. So this is the general definition of a vector in C2. We can have another vector ket phi that can be represented by the column vector C, D, where again C and D are complex numbers. Now it is possible to define inner products. So since we have two vectors, it is possible to define an inner product in two forms. I can do ket phi psi or ket psi phi. So this is how we read it. We read this expression from left to right. So when I say, not ket bracket phi psi. So when I say bracket phi psi, it means bra phi is multiplied with ket psi. And when I say bracket psi phi, I mean bra psi is multiplied with ket phi. So let us see how the first expression is multiplied. So that, as Professor Gangopadhyay mentioned before, this is directly matrix multiplication. So bra phi will be the transpose of this column vector with each of the elements taken, the complex conjugate taken. So we will have C bar D bar multiplied with AB. So that will give us this number, that is A C bar plus B D bar. This is a single complex number. Similarly, we can perform the necessary matrix multiplication for bracket psi phi. So the answer we will get in that case will be A bar C plus B bar D. Now we can observe and see that this complex number that we have obtained here is the complex conjugate of the complex number that we previously got. So bracket psi phi is equal to bracket phi psi conjugate. So this is the connection. This is an important property of inner products. So this is something that is good to know. Although we will be using very little of this, but this is an interesting property to know. When we have two vectors in C2, we can take two possible inner products and they are related to each other through the complex conjugation operation. Now we are considering the inner product of a vector with itself. So this is bracket psi. So as Qsim was defined as AB, we will essentially have A bar plus B bar. We know A bar is modulus of A squared and B bar is modulus of B squared. So this is the property of complex numbers. So the square root of this quantity is called the norm of a complex number. This was also defined in the previous session. So this is the square of the norm of a complex number. And remember, now what I'm stating here, I will kind of come back to this statement again further down the line. A given vector Qsim is a qubit state if this inner product is equal to 1. So if bracket psi, that is mod A square plus mod B square is equal to 1, then a given vector in C2 is said to be a qubit state. So what if I have a vector that does not have this property? What do I do? Well, it's quite simple. What we can do is, we can, whatever this number is, so let there be a general vector phi that, may not have this property. So what we will do is, we will kind of perform a transformation and get this new state, phi tilde, that is defined as follows. So first, what I will do is, I will calculate the inner product of phi with itself. So I will evaluate bracket phi. I will take the square root of that and I will divide ket phi by that complex number. Now we can take the inner product of this new vector with itself and it can be verified that the resultant vector will always obey this property. This process is referred to as normalization, and the quantity used in the normalization of a vector is called the norm. If it already had this property, this number would have been 1, and therefore phi tilde would have been ket phi tilde would have been equal to ket phi. So the formal definition of qubit states, they are vectors in C2, that is C cross C, with a unit norm. Could I calculate this in a new slide? Unfortunately, I do not have the tools to write these things. I will maybe include it in a write-up at a later point. However, since all of these, since all of these quantities are kind of defined here, I would kind of encourage you to do the calculations yourself as a practice. So now, again, we come back to the concept of basis. So we have defined ket 0 as the column vector 1, 0 and ket 1 as the column vector 0, 1. And ket psi can now be written as a ket 0 plus b ket 1. So if I have ket psi that was previously defined as column vector AB, now in terms of the basis ket 0 and ket 1, it can be written as a ket 0, b ket 1. Since we can write column vector AB in terms of a ket 0 and b ket 1, this basis is referred to as the standard basis. In terms of the the domain of quantum computing, this is also referred to as the computational basis. In general, in linear algebra, such bases are known as standard basis. So now so since this is a basis, this set forms a basis. When we consider all possible linear combinations, like all possible values of A and B, what we will get are all possible vectors in C2. Therefore, it is that this set spans C2. Now, using this and the definition of the inner products, this was also calculated in the previous session, we can see that bracket 0, 0 is equal to bracket 1, 1, which is equal to 1. Bracket 0, 1 is equal to bracket 1, 0, which is equal to 0. Any two vectors that follow this property are said to be an orthonormal basis because their norm is 1, they are unit norm, and they are orthogonal to each other. Like any pair of vectors that obey this property are said to be orthogonal. If they additionally obey this property, they are called orthonormal bases. Now, of course, each element of the orthonormal basis are valid qubit states, because why? They have a unit norm and they belong to the vector space C2. So since they are a unit norm vector from C2, they are valid single qubit states. Now this again was done before, so I'm going to move relatively quickly through this. If we evaluate the quantity bracket 0 psi, we will get A, and if we evaluate the quantity bracket 1 psi, we will get the quantity B. So this matrix multiplication has been performed here. Now, so we know that if we have a basis ket 0 and ket 1, then these corresponding inner products actually give us the coordinates of the vectors. Now, why am I calling them coordinates? Because of course, if I represent a vector as column vector A comma B, A and B by definition are the coordinates of that vector. So the coordinates are given by this inner product, these two inner products. So the coordinate corresponding to ket 0 is bracket 0 psi. The coordinate corresponding to ket 1 is the inner product bracket 1 psi. Therefore, we can, instead of writing ket psi as A ket 0, B ket psi, we can write it as bracket, like we can substitute A and B with the respective inner products. So I can write ket psi as bracket 0 psi ket 0 plus bracket 1 psi ket 1. So this is another way of representing the qubit state in terms of the basis. So now if you can see in this particular equation, I'm no longer referring to the complex numbers A and B. So any general quantum state, if I'm given a basis, can be expressed in this basis, in that basis using this property. So if I was given a different basis, say ket, V1 and ket V2, that is an orthonormal basis. As long as it is an orthonormal basis, in fact, as long as it is an orthogonal basis, but right now we will stick to orthonormal basis. As long as we are given an orthonormal basis ket V1 and ket V2, I can simply substitute ket 0 and ket 1 over here by the respective basis vectors ket V1 and ket V2, and using that any vector ket psi can be represented using this equation. Again, many of these things are not required for designing or developing quantum algorithms, but these are the basics. And since the only things that we know for sure right now are the basics, I'm discussing these concepts. So there are other possible bases that can also exist. So these two vectors, ket plus, ket minus, which has been described as the Hadamard basis, are given by these two column vectors. So yes, now ket psi can be represented in the Hadamard basis using this expression, similar to what we did with the computational basis or the standard basis. So in that case, the coordinate values as derived yesterday will come to be A plus B by square root 2 and A minus B by square root 2. So in this basis, the coordinates will take these values. Now we are coming back to the notion of photons. Now, whatever mathematics that we described before, now we are going to kind of try to put all these things together and describe what happens when a single photon is incident on a polarizer. Again, I'm kind of reiterating what I did yesterday, but the aim here is to repeat this as many times as it is necessary for everyone to understand. And people who are viewing the recorded version of this can see it multiple times so that these concepts are impressed upon enough number of times. So if we have an obliquely polarized photon, ket chi, so I'm using the Greek letter chi here, as cos theta, sin theta. So this is oriented at an angle theta from the vertical. So this can now be represented by cos theta ket 0 plus sin theta ket 1. And now, if there is a vertically aligned polarizer, that is a polarizer aligned along ket 0, then the probability of transmission is given by mod cos theta squared. Now, mod cos theta, what is it? It is ket chi, like the inner product bracket 0 chi. So that is this quantity. So it is the mod squared of this number. So the transmission probability is the absolute value squared of the inner product with respect to that basis element. Now, in general, whatever basis and whatever polarization state we consider, and whatever orientation of the polarizer we have, as long as we know the corresponding vectors to those polarization states, we can simply take the inner product, take the absolute value of it, and the square of the absolute value will give us the probability that a measurement in that basis will give that basis element as the outcome. So that is what is mentioned in the final statement. The above result can be generalized to transmission probabilities for a polarizer oriented along any direction. So as discussed in the previous session, these inner products give the coordinates of the vectors. And these coordinates tell us, like, contain the information of the measurement outcome probability. Like, if I perform a measurement with respect to this basis, I will get an outcome of ket 0 with a probability mod squared of this number. I will get ket 1 with a probability mod squared of this complex number. Now, why is this so? There is no answer to that question. In fact, that question is technically not meaningful because the theory was designed to be this way. In fact, this, as someone asked during the earlier session, there was a question. Someone asked, like, what is the bond rule? So the bond rule is essentially the rule that states that this number gives the probability of a measurement outcome. So this was formalized by Max Born, who was a German physicist, and the theory was built around this assumption. So the theory was built so that measurement outcomes are given by this number. So this is happening by design. Like, we have built this theory to explain what is physically happening in the interaction of a photon with a polarizer. So now we shall take a further step back and look at complex numbers. So in general, a complex number can be written as x plus iy. It can also be represented in terms of the polar coordinates as z is equal to r e to the power i5, where I is, the square root of -1. It is the fundamental imaginary number. So where r is given by square root of x squared plus y squared, and phi is the inverse tan, like arctan is tan inverse of y by x. So this angle is tan inverse y by x. That can be seen by the trigonometry, because the side opposite to that has length y and the side adjacent to this angle has length x. And of course, the hypotenuse is square root of x squared plus y squared. This is given by r. So this comes from basic trigonometry. So any complex number can also be represented in the polar form. Now, why am I doing this? We will see. So this slide, we shall talk about what is known as the global phase. So this was referred to in yesterday's session, but much explanation was not given. This slide is dedicated to that. So consider the unit complex number, e to the power i5. Now this is called a unit complex number because the magnitude of this complex number is 1. R is equal to 1. Yeah, in this notation, R is the modulus or the magnitude of the complex number. So when R is set to 1, this is called a unit complex number. It is also in certain cases referred to as a phase factor. Now these things will actually appear a lot in our subsequent discussions. So kindly pay attention to this. Now let us say we have a photon state ket psi as defined in the previous slides, and I'm multiplying it with a unit quantum number. Unit phase factor. Now this quantity, I have multiplied it to the entire state vector, to the entire ket vector. Now this factor is called a global phase factor. Now when I take a projection, now what is a projection? A projection is an inner product. So when I take the projection of this basis, state, e to the power i5 times ket psi with respect to a basis vector, say ket 0, we will get this quantity. Essentially, this is a number, so I can just pull this number out and I will have this quantity here. Bracket 0 sign. Now, as a complex number, of course, this number is different from just this because I've multiplied another complex number. But if I take the probability, now what is the probability? The probability is the, the probability is the modulus of this number times like square. So if I take the modulus of this quantity and square it, what will essentially happen is when I take the modulus, this is a unit complex number. So when I take mod squared of this whole expression, it will be the same as mod squared of bracket 0 sign. So what essentially happens is if I multiply a given quantum state by a global phase factor, even then the measurement probability with respect to a given basis state does not change. It will have the same transmission probabilities that of Qsim. So it is not possible to distinguish this quantum state e to the power I5 Qsim from Qsim by performing only polarization measurements. If I have a polarizer, both of these states will have the same probability of passing through the polarizer. That is why we say two quantum states differing from each other by a global phase are considered to be equivalent. They are considered to be identical. So this is the entire principle and property of the quantity called global phase. A global phase is a unit complex number that multiplies itself to a quantum state. Right now we are talking about a single qubit state. When we go to multi-qubit states, the same rule applies. So the global phase rule is true for single qubit and multi-qubit states. The only important thing to be noticed is the unit complex number should be multiplied to the entire state vector. So now let us write the state Qsim, which in our previous slides we represented as we represented it as A times Q0 plus B times Q1. Now let us represent it using polar coordinates. Let us say A is equal to R0 e to the power I phi 0 and B is equal to R1 e to the power I phi. So Qsim can now be written as this. Now what I can do is I can take this quantity e to the power I phi common because it is just a number. So I can pull it up because right now I'm just adding two vectors. So if I take that out, what happens is I have R0 Q0 where R0 is a real number and R1 e to the power I phi 1 minus phi 0 Q1. So now Qsim is equal to e to the power I phi naught times this new vector. This quantity, this unit complex number is multiplying this entire state vector. As discussed in the previous slide, two states that differ from each other by a global phase are considered to be equivalent. Therefore, Qsim is considered to be equivalent to the state. Observe that this is not an equal to sign, this is an equivalent sign. Qsim is not equal to this state, it is equivalent to this state. I cannot perform measurements and distinguish these two states. Therefore, Qsim is equivalent to R0 Q0 plus R1 e to the power I phi 1 minus phi 0 times Q2. Now I can replace this variable phi 1 minus phi 0 by a new variable phi and I can write Qsim as R0 Q0 plus R1 e to the power I phi Q1. Now I'm writing an equal to sign here, but it should be an equivalent sign. And now we can measure the inner product to see what happens. Originally, Qsim is a qubit state. That implies mod squared A plus mod squared B is equal to 1. We see that the same property is satisfied here also. Why? Because mod squared A is R0 squared and mod squared B is R1 squared. So even in this case, when I take the inner product of this vector with itself, we will get R0 squared plus R1 squared and the inner product is 1. So this is also a valid qubit state, single qubit state. Now, why did we do this transformation? Well, we know that these quantities, since sum of their squares, like this looks like the equation of a circle. Like this can be seen as the x coordinate, this can be seen as a y coordinate. So since the sum of their squares is equal to 1, and we also know that this is the magnitude of a complex number. So from this definition here, we know that the value of r is always going to be positive. So we know that R0 and R1 lie between 0 and 1. And we also know this. So we can represent R0 by cosine theta by 2 and R1 as sine theta by 2. Now, why did I take theta by 2? You will see shortly. Where, now since I'm saying they can only lie between 0 and 1, this angle in here can vary from 0 to pi by 2. Because that is where cos and sine are, positive, and they vary from, 0 to 1. So since I've written theta by 2 here, theta can vary from 0 to pi. Now, e to the power I5, here this number phi can vary from 0 to 2 pi because e to the power I 2 pi is 1. So this quantity here has a periodicity of 2 pi. So this space factor, this is also a unit complex number. This does not appear here, it is only appearing here. Now this space factor is not multiplied to the entire qubit state. This is only multiplying with one of the components. So this, in this case, this phase factor is known as the relative phase. So this is the relative phase. So a phase that multiplies the entire qubit state is the global phase, and a phase that appears inside the expansion of the qubit state is a relative phase. Now, based on this angle selection, it is actually possible to use. So now what is happening? Both R0 and R1 are represented by a single parameter theta, and the relative phase is represented by a parameter phi. With these two choices, we can now write ket psi as cos theta by 2 ket 0 plus e to the power I5 sin theta by 2 ket 1. Now, why did I choose these particular ranges? Because in this range, it is possible to represent this ket psi as a point on a sphere of radius 1. Now, what does that mean? It means this. So when I write, a quantum state to be ket psi is equal to cos theta by 2 ket 0 plus e to the power I5 sin theta by 2 ket 1, what is happening? I'm representing this state. Now again, this is just a mathematical representation. This is good for visualization. We are representing it as a point where theta is the angle from the z-axis and phi is the angle from the x-axis. So phi is the azimuthal angle and theta is the altitude or the declination. So why was this done? Because this is a geometric representation of the qubit state, and this geometric representation, this sphere is called the block sphere. This image is from Wikipedia. So now what about the common states that we know? What about ket 0? Where will that be on the block sphere? Of course, I've drawn it here. But for a better illustration, if we have a sphere, the blocks ket 0 is the north pole of the block sphere. Like if I'm assuming the vertically up direction to be the north direction, then the north pole of this sphere is ket 0. Ket 1 is the south pole. Every other linear combination will be represented by a point on this block sphere. So if we look at ket plus, it is actually 0 plus 1 by root 2. So for that, we can go back here and see what is the right choice of the angle. We will know that for theta equal to pi by 2, I will get cos pi by 4 and sin pi by 4. Both of these are 1 by root 2. So I will get 1 by root 2 ket 0 plus 1 by root 2 ket 1. I can set phi equal to 0, in which case this quantity will become 1. So for a choice of theta equal to pi by 2 and phi equal to 0, we will get the state ket plus. So that is essentially what is represented here. This is making an angle 0 degrees with the x-axis, so phi is equal to 0, and it is making an angle. So since this is the z-axis and this is the x-axis, the angle between these two lines is 90 degrees. So for these two choices, we have this k plus k. Like this, we can represent all vectors on the block sphere. Further properties of the block sphere we shall discuss next week. With this, I will end my session now. We still have 15 minutes. So what I'm going to do is, for the coming 15 minutes, I shall take questions. And so I will only be looking at questions that are being posted from this point. It is 12:44 now. I will only start reading questions from this time code. Kindly post your questions. If you have posted it before, repost them. Just post them once. I will read through all of them. All right. So with this, I think I come to the end of my session. I will leave the slides up here nonetheless. So yeah, let me open the chat. Yes. So please show how to execute these polar coordinates in Qsim. Yes, we will show that next week. So right now, I just wanted to introduce these things. We didn't want to do too many things in the first week itself. Don't worry, everything that we are explaining here, we will show you how to do it in IBMQ. We will show you how to do it on Qsim. Wherever the features are available, we will show you how to use them. So please be patient. Remember that this is a 4-week course. So we are only in week 1. We are just 25% done. 3/4 of the course is still left. Yes, so Ayush Sharma has asked, in case of polarizer, we basically shot photons on it and calculate the probability of the polarization state aligned in the direction of the polarizer. So is the probability our output or something else? Okay, technically speaking, in that experiment, the output is whether the photon is coming out or not. It is a yes or no question. When I'm shooting a polarization, thank you for using that word. When I'm shooting a photon at a polarizer, the question is the photon going to come out on the other side or is it going to get absorbed? The answer may be yes, the answer may be no. The probability is the probability of the answer being yes. So if I'm shooting multiple photons of the same polarization at a polarizer that is at a fixed orientation, then the probability of the photons getting transmitted, the probability of me saying yes, the photon will pass through, or me observing that yes, the photon has passed through, is given by, if the polarizer was originally aligned along ket 0, then it is given by bracket, it is given by this number essentially. Let me show that in the slides. It is given by this number over here. If it was some other state, I will just replace this bra 0 by that state. Okay, so Pankaj Gupta has asked, ket 1 is the opposite end. Yes, it is. In general, if you have two orthonormal states, they will always be at opposite ends of the block sphere. We shall see about that, in like these properties we shall discuss later. Can I make a Discord server? Yes. So, okay. So let me address this briefly. We need multiple things for a Discord server. We first need a premium account, and to run any good Discord server, the most important ingredient are moderators. So right now I'm hunting for moderators. Like I cannot, individually moderate a Discord server with potentially thousands of members. So I'm hunting for mods. Once I get enough mods, we'll make a server, and we can interact on Discord. Okay. So yeah, how is this measurement, which is a qubit? Okay, measurement is not a qubit. Measurement is the experiment. When I shoot this is one particular instance, there can be several such instances. When I'm shooting my photon, to borrow the vocabulary of Ayush Sharma, when I'm shooting my photon at the polarizer, that experiment, that entire experiment is the measurement. And the outcome of that measurement is stored in the classical bit. So the measurement itself is not the qubit. The qubit undergoes a measurement. The measurement is a physical process. Why have we taken theta by 2? If I took it as theta, then I would not be able to use the whole sphere. I took it as theta by 2 because I wanted to use all points on a sphere. A sphere is a very, nice object. It is very pleasing to look at. And more importantly, Felix Bloch defined it this way. So that is called the Bloch sphere in honor of the physicist Felix Bloch. I think he was German. So it is his notation, and we are just using his notation. So then we have Parth, who's asked, what is the relation between global phase phi and polarization angle theta? Oh, okay. So there is no relation between global phase and the polarization angle. However, if you notice here, if we are treating this as the polarization state, if this is vertically polarized, if this is horizontally polarized, if I want to make this side 0, then theta will be set to 0. So this quantity will vanish and cos theta by 2, sorry. Oh, no. I have to set theta to be for this, I will have to set theta to be, yeah, pi by 2. I'm sorry. But in that case, what am I saying? I'm sorry, I just got confused. Oh, yes. If I set theta to be 0, yes, sine 0 will become 0 and cos 0 will become 1. So it is the polarization angle is not related to the phase factor. It is actually related to this angle theta. In fact, the polarization orientation that we discussed before, it will be twice this angle. So if my polarizer is oriented at 90 degrees to the vertical, then that will correspond to theta by 2 having a value of pi. Like theta by 2 having a value of pi by 2. So theta will have a value of pi. So the polarization angle is related to this theta here. Okay, so yeah, I know the variables are kind of coinciding, but since Bloch sphere is visualized in terms of theta and phi, I use that. So the theta that we used for oblique polarization now becomes theta by 2. So when we go to orthogonal states, we go from 0 to 90 degrees. In this case, when we go to orthogonal states, since we have replaced theta by 2, we will go actually from 0 to 180 degrees because we have scaled the angle by a factor of half. Please explain the Bloch sphere again. So there is not much to explain here. We will do it, we will cover it again next week, and of course the recordings will be up, so please go back and see the recordings. How to choose correct or valid qubit state? Any point on the Bloch sphere is a valid qubit state. There is no need to be correct about it. So that is the whole point of defining the Bloch sphere. Every point is a unique qubit state. So what is a state vector? A state vector is the state. Like when I say state vector, it is the vector representing the state. As I said in the initial slides, these vectors can be used to represent different physical quantities. In the example that we have discussed so far, we are representing the polarization of a single photon using these vectors. It is possible to use these same vectors to represent a wide variety of physical quantities. We shall discuss more about that later. Rohan has asked, is the Bloch sphere related to the Fermi sphere? No, they are not. The Fermi sphere is used in statistical physics. Bloch sphere is essentially, was originally used to describe phenomena in optics, and it has been carried over to quantum computing as well. What is the need of the complex representation? Well, since our vectors have complex coordinates, we need complex representation. Attendance link is available. This course has no attendance. You can, either attend the session or you can view the recordings. Could I explain normalization once more? Yeah. So let me go back to that slide. So if a vector has this property, if its norm is 1, then it is a qubit state. Now, what will I do if a vector does not have norm 1 and I want to convert it into a qubit state? What I will do is I will calculate its norm, which is this number, and divide the vector by the square root of the norm. So what will happen? When I take the inner product of this vector, like I intentionally left this not worked out because usually when I discuss this with students or people who are attending, I encourage them to do this calculation. So what I will tell is I will tell you to do the same thing. Ket phi has been defined here. And I have told you how to calculate the inner products in this slide. So just find this vector using this formula and evaluate the inner product of ket phi tilde with itself and see if it comes out to be 1. Right. Okay. Consider this to be an unofficial assignment. This is not an official assignment. You don't have to submit or anything. Just try it to satisfy your own curiosity. So that is normalization. If measurement value is 0, what is the probability to normalize? Okay, so as I mentioned before, the measurement value just denotes the outcome of an experiment. The measurement value is not the coordinate. If the value of B is 0, then a measurement will never give me the outcome ket1. That is it. So these coordinates, if they are, ultimately when I'm normalizing, I'm taking mod A square plus mod B square. Both of these cannot be simultaneously 0. If both of them are simultaneously 0, then my vector itself becomes the null vector or the 0 vector, in which case it is no longer a unit norm vector, and therefore it is not a valid quantum state. So we are only concerned with vectors that have a finite norm. The null vector is, it's a 0 vector. It does not represent any physical state. Can we send data through qubits in optic fiber? Yes, as I mentioned yesterday, photon polarization qubits have been used to transmit data, although nowadays different other qubits are generated, and yes, it is possible to transmit qubits, certain qubits, not all, some qubits through an optic fiber. Yes. Pankaj Gupta has asked, can the same block sphere be made for ket plus and ket minus? Yes, indeed. As I showed before, ket plus is this point. Now, since ket minus is orthogonal, now we know that this is the relation between ket 0 and ket 1. Ket 0 is up, ket 1 is down. And I've shown ket plus is here. So you can guess ket minus, is in the opposite direction. It is an arrow pointing from the origin to this direction. So it is this point on the sphere. Similarly, you can see ket I and ket minus I, what they are. Like, I again encourage you to look at this formula, find the appropriate values of theta and phi, and locate the points on the sphere. Visualizations will be shown next week for all of these states. Slides will be shared. Do not worry, Keval Joshi. Dr. Nagvendra Kumar has asked slides and videos. The videos are on the YouTube stream link. They have been emailed to you. So just go back to the stream and view any point of this video that you want. Slides, again, as I mentioned before, will be uploaded. Is there any project at the end of the course? Again, we do not have the manpower to implement a project and evaluate all of you guys. So I don't think there will be a project. We will have some assignments and maybe a minor quiz or something like that for certification purposes. Please explain the mathematics again. Go back to the YouTube video and follow the explanation again. Today, I think I spoke slowly enough, so you should be able to follow what was done. And I encourage you to do the calculations by hand. How is this different from boson computer technology? I'm not aware, by what you mean by boson computer technology. If you are referring to some kind of computers that leverage like anionic quantum computers or something like that, then I don't know, that is a thing. I'm not familiar with this term boson quantum computer. So yeah, apologies for that. 1 second, please. So yeah. Just 1 second, let me stop. So I will answer questions for another 2 or 3 minutes. Yes, so there are 2 questions from Subimal Dev. Measuring photons using a polarizer. If the photon passes through, it is detected. If it is absorbed, it is not detected. Well, if it is absorbed, it is not detected. Therefore, that is also a detection. It's a negative detection. How do we account for the absence? Well, we account for the absence by noticing that there is no photon. And if it has been absorbed, then it definitely measured to be in the like polarization state that was orthogonal to the orientation of the polarizer. It would be nice if I explain the orientation of Ket0 and Ket1. Now, Ket0 and Ket1 I explained in the previous session what they are. So I request you to go back and see the previous videos. Today you will get the slides. So after that you can kind of read through them, and it would be, I think the explanation should be apparent from that. Ayush Sharma has once again asked, if the output is yes or no, then isn't the corresponding, is it corresponding to classical output? Yes, it is. The measurement of a quantum experiment is always a real number. In the case of a qubit, it is a single classical bit. So measurement outcomes are always going to be classical because we interpret the universe, the world that we see classically. So I can mathematically represent a photon polarization state on a Bloch sphere, or I can use complex numbers to write it. I can write it as a column vector. But as I mentioned before, I can never see that photon. If there is an electron having a certain spin orientation, we can never see that electron having that particular spin orientation. Like quantum information manifestly is not accessible to us. We can only access it by probing the system, which will inevitably lead to a measurement, and the outcome of a measurement is always going to be in the classical domain. So this is kind of, a quantum to classical transition. Studies in this are ongoing, but the basic convention of quantum mechanics, at least as far as we agree so far, is set up like this. Measurement outcomes always come to the classical world. The quantum state exists in the quantum world. So there is kind of a quantum to classical transition that happens when we perform a measurement. Yeah, so Anandraj has asked, can you understand operations like addition, subtraction, multiplication, matrix operations in terms of normal decimal values or binary values? What is the operational difference between these? Okay, so right now, wherever we are using addition or multiplication, it is kind of implied. So if we are adding two vectors, we are doing vector addition. If we are adding two complex numbers, it is complex number addition. Binary number math we have not done so far, so you don't have to worry about it, at least for now. Next week onwards, we shall be doing a little bit of that. But right now, it is kind of understood. I hope that answers your question. So Keval Joshi has asked, we are checking the photon crossing over the polarizer. We are quantifying the probability of getting the photons through it, but are we concerned to check the quality of the photon? What do you mean by the quality of the photon? Like, I'm unable to understand that. Like, a photon is a photon. So it's actually theoretically impossible to alter the quality of a single photon. If there is a collection of photons, maybe we can do something to alter their quality, but a single photon is a single photon. Sure, we can change some of its properties, but the photon remains a photon. So I'm sorry, I do not understand the meaning of this question. Maybe when I scroll down, we can see if you have mentioned this question again. Again, I urge you guys to just post your question once. You don't have to post it once privately and once on the open channel. Just post your question once, whether you are sending it to me privately or on the public chat. As you can see, the more questions you repeat, the slower I will be scrolling down and the lesser questions I will answer, because in a couple of minutes I will stop answering questions because, of course, I have other things to do in the day and this session cannot run forever. So Ayush Sharma has, repeated the question again. Sir, when you got confused, we do not feel alone. Yeah, so yes, when I was thinking about the trigonometry angles, my brain just turned off for a second. How the swarm optimization can be used? I do not know what swarm optimization is, Deepthi. I'm sorry, it's beyond my knowledge. How many basis vectors are there in the Bloch sphere? Okay, So let me answer this question. So this is from Pavitra B. Let me be precise here. Those who are in the session, kindly pay attention. Those who are viewing it in the recording, this is important. A basis is a set. So depending on the dimension of the vector space, the number of vectors in that set will vary. Right now, a qubit belongs to a vector space that has two complex dimensions. So a complex, like there will be two basis vectors in a single basis. In the block sphere, I can define infinitely many such bases. When I'm talking about, when I'm saying using the word basis, I refer to the set. There can be infinitely many sets. Each of these sets, since the block sphere represents a single qubit state and that belongs to a two complex dimension space, each basis will contain only two vectors. And this is how the things are different. I hope this answers the question. How is this course helpful to a mechanical engineering student? I don't know. If you know of any mechanical engineering student attending this course, maybe at the end of the course, they can tell us how it was helpful to them, and then we will know. So right now, I cannot answer this question. Maybe some mechanical engineer who's present among us can answer this question at the end of the course. Parth has asked, e to the power I theta is used to rotate the vector on the complex plane and the final vector is different. Then why do we say global phase does not matter? The reason I'm saying global phase does not matter is that I am unable to, yes, you're right, it performs a rotation. And when I am rotating, so when you're talking about the complex 2D plane, that is actually just one complex number. So that 2D plane is one complex dimension. So it is rotating a single complex number. Now this global phase is multiplied to two complex numbers simultaneously. Remember, I did e to the power, let me just share my slides again. Yes, the chat window jumps out. Yeah, so as you can see here, e to the power I phi is multiplying itself to both the complex numbers a and b that are present inside Qsim. Remember, as I defined in the beginning of the slide, Qsim is given by this. Okay, yeah. In this presentation, whenever I refer to Qsim, I'm referring to this vector only. Whenever I'm referring to Qphi, I'm referring to this vector only. The notation across this entire set of slides is consistent. The only place where there may be an overlap is when I'm referring to the angles theta and phi. But in that case, I have made enough distinction so that people can differentiate. But Qsim and Qphi refer to these two vectors that I've defined beforehand. So when I'm multiplying a unit complex number, e to the power I theta or e to the power I phi to this whole thing, I'm kind of rotating both these complex numbers together. So the relative angle between them, the relative phase does not change. Since the relative phase does not change, the measurement with respect to a certain basis will have the same probability outcome. So when I'm multiplying a state with a global phase, I cannot, yes, they are different quantum states. I'm not arguing with that, but I have no means of distinguishing between them. So when I try to perform a polarizer type experiment, I will never be able to distinguish between them. Maybe at a later point, I will tell you where this global phase actually comes from. And then you will understand why it actually does not matter. Where you can get the notes, you will find out soon to Palab Sarfar. Sandhana has asked, by choosing a basis of only two vectors, are we restricting the size of the output vector space? Not exactly, because right now we are talking about the generalization of a classical bit to a quantum bit. So a single quantum bit belongs to this vector space. We are not choosing that. Since we are talking about a single quantum bit, this is the vector space we are working in. As we talk about multiple qubit states, we shall be referring to different vector spaces. That will be covered in the next week. So Sandeep Singha has asked, if you consider a photon as a single wave, then it passes through the direction of the optical axis. But why polarization of the photon is represented? So yes, it passes at the direction of the optical axis. I didn't know the photon has an optical axis. Materials have optical axis. I'm again sorry, I do not. This question is not very clear to me. But in general, the polarization is a vector. It's a vector on a plane usually for plane polarization. It says constant vector on a plane. So that vector can be decomposed in terms of components. So that is why each component is like I'm representing that polarization vector as a linear combination of the components. For circular and elliptical polarizations, those are kind of time varying vectors. So those vectors go round and round. For elliptical polarization, the length will also kind of change. For circular polarization, the length of that vector does not change. Okay. So book, it was mentioned in the previous session to Vishal Kumar Baid's question. The slides will be shared. So the book contains the necessary physics and the mathematics for this discussion. Avni Inamdar has asked, so whether a photon passes through a polarizer corresponds to the classical outcome 0 or 1. Yes, but when we do, yes, indeed, yes. So is this measurement of quantum experiment? Yes, it is a quantum experiment of the qubit, the result of which is a classical bit. Every experiment has some kind of an input and an output. The input is a photon having a quantum state, which is represented by a qubit. The experiment is shooting this photon onto a polarizer. The outcome is whether the photon passes through this polarizer or not. If it passes through, I'm representing it by the number 1. If it's not passing through, I'm representing it by the outcome 0. So yeah, the programming part to Manoj Kanani's question, we shall be covering more in the next week. So yeah, I have some feedback. Well, am I really what? Like the statement is not complete. Access to Qsim will be discussed at a later point in time. Why Z basis is the measurement basis, why another basis is not used. Maybe I will, so this is in regard to a question from Madhurima Das. Maybe I'll talk about this in the next week. Oh, am I really teaching beginners? Well, there is only so low I can go. Anything beyond that will make teaching kind of impractical. So, I mean, certain prerequisites were mentioned in this course. So people having that prerequisite can learn from this course. The rest, if you need any help in understanding something, you can contact us. We'll try to do our best. Beyond that, well, it is what it is. And of course, like attendance, this is a free course and you're free to join or leave whenever you please. I think, yeah, after this, there are a lot of thank yous. So I think this is a good point to call it a day. So I'm stopping the sharing. With this, we can conclude today's session. So yeah, if the host or the co-host is around,
Yes, sir, we are here and we can close the session for today.
Yeah, so I thank you all for listening on behalf of myself and Professor Gangopadhyay. We shall meet again next Saturday. Timings and details you will get to know. Any further updates, you shall be receiving emails on your registered email ID. So kindly check in on that. Yeah, and sorry for interrupting, Ms. Vandana. Please continue.
Thank you, Jyoti sir. I was thanking you that for a very informative session for our participants. Thank you, sir.
Yeah, all right.